welcome to this problem walkthrough. Today, we'll be exploring an interesting algorithmic challenge titled Minimize Deviation in Array. We'll take a deep dive into the problem, understand its requirements, and discuss efficient approaches to solve it. Let's get started. In this problem, you are given an array called nums that consists of n positive integers. The task involves performing specific operations on the elements of this array to minimize a value known as the deviation. Now, there are two types of operations you can perform. If an element in the array is even, you can divide it by 2 as many times as you like. For example, if you have the number 8, you can divide it by 2 to get 4, and divide it again to get 2. On the other hand, if an element is odd, you can multiply it by 2. For instance, if the number is 3, you can double it to get 6. Importantly, these operations can be applied to any element of the array, and you can repeat them any number of times. The ultimate goal is to minimize the deviation of the array, which is defined as the difference between the largest and smallest elements in the array. For input, you are given the array nums, where the size of the array, n, can go up to 100,000, and each element in the array can be as large as 10 to the power of 9. The output for this problem is the minimum possible deviation of the array after you've applied the allowed operations. To understand this better, let's look at an example. Suppose the input array is 1, 2, 3, 4. You can start by multiplying the number 1 by 2, which updates the array to 2, 2, 3, 4. Next, you can divide the number 4 by 2, giving 2, 2, 3, 2. At this point, the maximum element in the array is 3, and the minimum is 2. The deviation, which is the difference between the maximum and the minimum, is 3 minus 2, which equals 1. This is the smallest possible deviation you can achieve for this input. Now let's examine another example to see how the operations can be applied. If the input array is 4, 1, 5, 23, the process begins by multiplying the number 1 by 2, resulting in 4, 2, 5, 23. Next, you multiply the number 3 by 2, updating the array to 4, 2, 5, 26. Then, you divide the number 20 by 2, which changes the array to 4, 2, 5, 10, 6. At this point, the maximum element is 10, and the minimum is 4, so the deviation is 10 minus 4, which equals 6. However, with further operations, you can reduce the deviation to 3, which is the minimum possible deviation for this input. Let's consider one more example. Suppose the input array is 2, 10, 8. First, you divide the number 10 by 2, which updates the array to 2, 5, 8. Here, the maximum element is 8, and the minimum is 2, giving a deviation of 8 minus 2, which equals 6. Next, you divide the number 8 by 2, resulting in 2, 5, 4. Now, the maximum element is 5, and the minimum is 2, so the deviation is 5 minus 2, which equals 3. This is the smallest possible deviation for this input. Finally, let's discuss the constraints and some edge cases. The array size, n, can be as large as 100,000, and the values in the array can go up to 10 to the power of 9. This means the solution must be highly efficient to handle large inputs. For edge cases, consider a single element array. Here, the deviation is always 0 since the maximum and minimum are the same. If all elements in the array are even, you can repeatedly divide each one by 2 to reach their smallest possible values and minimize the deviation. Similarly, if all elements are odd, you can first convert them to even by multiplying each by 2, and then proceed to minimize the deviation. These scenarios highlight the importance of understanding the operations and their effects on the array to achieve the optimal result efficiently. To solve the problem of minimizing the deviation in an array, we aim to reduce the difference between the maximum and minimum values in the array. The operations allowed are dividing an even number by 2 or multiplying an odd number by 2. These operations help us dynamically adjust the range of the array. When considering the solution, we have multiple approaches. A brute force method is one option, where we explore every possible sequence of operations. However, this is computationally expensive. To address the problem more efficiently, we can consider optimized strategies that leverage data structures like heaps. By thoughtfully analyzing the constraints and operations, we can narrow down our approach to one that balances efficiency and correctness. One approach is the brute force method. The intuition behind this is straightforward: apply all possible sequences of allowed operations on each number in the array, calculate the deviation for each resulting combination, and identify the minimum deviation. The implementation involves generating all these combinations, which quickly becomes computationally expensive. With n elements and multiple states for each element due to the operations, the number of possibilities grows exponentially. As a result, while simple to conceptualize, this method is infeasible for larger input sizes. To improve on this, we can use an optimized approach that leverages priority queues, or heaps. This method focuses on dynamically adjusting the maximum value in the array to minimize the deviation. The idea is to first expand all numbers to their largest possible states, meaning odd numbers are multiplied by 2 to ensure consistency. Using a max heap, we can efficiently track and update the largest value, repeatedly dividing it by 2 if it's even, and recalculating the deviation at each step. This process continues until further reductions are no longer possible, resulting in a significantly faster solution. The heap-based approach strikes a balance between efficiency and correctness. By always targeting the largest value in the array and making decisions dynamically, it avoids the computational explosion of brute force. This strategy is particularly effective because it uses a max heap to quickly access and update the largest number, allowing us to iteratively reduce the deviation. Additionally, by converting all odd numbers to even at the start, we ensure that all potential reductions are explored. This method aligns well with the problem's requirements. The chosen strategy uses the heap-based approach for several key reasons. First, it is significantly more efficient than brute force due to the logarithmic operations of the heap. Second, it aligns intuitively with the goal of minimizing deviation by focusing on the array's maximum value. Finally, it incorporates key observations, such as the need to expand odd numbers initially and the importance of tracking both the maximum and minimum values to calculate the deviation. Alternative approaches, such as sorting the array after every operation or generating all possible states, are computationally prohibitive. These methods lack the adaptability and efficiency of the heap-based solution. While brute force guarantees correctness, the exponential time complexity makes it impractical for real-world scenarios. The heap-based solution, on the other hand, offers an optimal trade-off between performance and correctness. While its implementation is slightly more complex than brute force, this added complexity is justified by the significant improvements in runtime. This approach ensures scalability to larger input sizes while maintaining accuracy, making it the most practical choice for this problem. To solve the problem of minimizing the deviation in an array, we need to first understand the operations allowed and their impact. Specifically, the two key operations are dividing even numbers by 2 and multiplying odd numbers by 2. These operations give us control over the range of values in the array. The objective is to minimize the difference between the largest and smallest values in the array after applying these operations strategically. To begin, we pre-process the array by converting all odd numbers to even. This is because odd numbers can only increase when doubled, so converting them to even helps us explore their maximum potential values first. Once the pre-processing is complete, we use a max heap to efficiently track and manage the largest value in the array. Since most heaps in programming libraries are implemented as min heaps, we simulate a max heap by storing negative values. This allows us to extract the largest value quickly while maintaining the structure necessary for our algorithm. After setting up the max heap, we need to keep track of the smallest value in the array during pre-processing and throughout the iterations. This is crucial because the deviation is calculated as the difference between the current maximum and this minimum value. Now, we iteratively minimize the deviation. While the largest value in the heap is even, we repeatedly extract it, calculate the deviation, and reduce the value by dividing it by 2. The reduced value is then pushed back into the heap as a negative number to maintain the max heap property. During this process, we also update the minimum value if the reduced value is smaller than the current minimum. This ensures that our deviation calculations remain accurate. The iteration stops when the largest value becomes odd since we can no longer divide it further. At this point, we calculate the final deviation using the last maximum and minimum values tracked. The approach we've outlined relies on a few key insights to ensure it's both efficient and correct. First, converting odd numbers to even at the start is necessary because it allows us to explore the maximum possible range for each number. This ensures we don't miss any potential states that could lead to a minimized deviation. Second, the use of a max heap is critical because the deviation is determined by the largest and smallest values in the array. The max heap lets us efficiently extract and modify the largest value at each step, which is central to the algorithm. Finally, dynamically tracking the minimum value ensures that the deviation calculation reflects the true difference between the largest and smallest values as we iterate through the array. These insights form the foundation of the algorithm and guide the decisions made in each step. The algorithm relies heavily on specific data structures to achieve efficiency. The max heap, simulated using a min heap by negating values, is the backbone of the approach. This data structure allows us to efficiently extract, modify, and reinsert the largest value in the array. Alongside the heap, a variable is used to track the smallest value in the array. This variable is updated dynamically during pre-processing and iteration, ensuring that deviation calculations remain accurate. The key operations involved are heap insertions and extractions, which are performed in O log n time. Each number in the array may be divided multiple times, but only while it remains even. This iterative reduction ensures that the largest values are explored thoroughly, and their impact on the deviation is minimized step by step. The algorithm's complexity is determined by the combination of pre-processing, heap operations, and iterative reductions. Pre-processing the array to double odd numbers and build the heap takes O n time. Heap operations, which include inserting and extracting elements, are O log n, and are repeated for each element in the array. Since each number can be reduced by a factor of 2 at most O log max underscore element times, the total time complexity becomes O n asterisk log max underscore element. In terms of space, the heap requires O n storage, making the overall space complexity O n. To illustrate, consider the input array 1, 2, 3, 4. After preprocessing, the array becomes 2, 2, 6, 4, and the max heap is initialized as -6, -4, -2, -2. The minimum value is set to 2. In the iterative process, we reduce the largest value step by step, updating the heap and recalculating the deviation. The final deviation, after all reductions, is 2. This example demonstrates the algorithm's efficiency and correctness in minimizing the deviation. To solve the problem of minimizing deviation in an array, we start by importing the heap module, which helps us efficiently manage a priority queue. First, we define our solution class and the minimum deviation method. The initial step is to normalize the input array. Here, we iterate through each number in nums and ensure all numbers are even. If a number is odd, we multiply it by 2 to make it even. This is because even numbers can be divided by 2, giving us more flexibility when adjusting the values. Once normalized, we push the negative of each number into a heap. This is done because Python's heap is a min heap by default, and by using negatives, we simulate the behavior of a max heap. After this, we initialize two variables, min_val, which tracks the smallest value in its current form, and min_deviation, which starts with infinity as we aim to minimize it. Next, we enter a loop where we repeatedly extract the maximum value from the heap, convert it back to positive, and calculate the deviation by subtracting min_val from this maximum value. This deviation is checked against min_deviation, and we update the latter if the current deviation is smaller. If the maximum value is odd, we stop the process as odd values cannot be divided further. When the maximum value is even, we continue by dividing it by 2, as even numbers allow further reduction. This new value is then pushed back into the heap, ensuring that the heap remains updated with the adjusted value. We also check if this new value is smaller than min_val, and if so, we update min_val to reflect the new minimum value in the array. This process continues until the loop exits, either because the maximum value becomes odd or no further reduction can be made. Finally, we return min_deviation, which now holds the smallest possible deviation achieved through the described operations. This approach ensures that we systematically reduce the array's range while maintaining efficiency using the heap data structure. Here, we begin by importing the necessary utility classes and defining our solution class. The goal of the minimum deviation method is to minimize the deviation in the given array. To start, we normalize the array by ensuring all numbers are even. This is because even numbers can be halved, while odd numbers must first be converted to even by multiplying them by 2. We use a max heap, implemented via a priority queue with a reverse order comparator, to keep track of the largest elements efficiently. Alongside, we maintain a variable minval to store the smallest value in the array during this process. As we iterate through the array, each number is either doubled if odd or added directly to the heap if already even. Simultaneously, we update minval to ensure it always holds the current minimum value in the array. After normalizing the array, we proceed to minimize the deviation. The variable min deviation is initialized to track the smallest deviation encountered. In a loop, we repeatedly extract the largest value, maxval, from the heap and calculate the deviation as the difference between it and minval. If the largest value is odd, we stop, as odd numbers cannot be halved further. Otherwise, we have the largest even value and add it back to the heap. This step ensures that we explore smaller values for the largest number while potentially updating the global minimum value, minval, if the halved value is smaller. The loop continues until no further halving is possible, and finally, we return the smallest deviation found. To solve this problem, we start by normalizing the array. The goal of normalization is to ensure all numbers are even since even numbers can be halved, reducing their value while maintaining flexibility in adjustments. For example, in the array 1, 2, 3, 4, odd numbers are multiplied by 2, resulting in the normalized array 2, 2, 6, 4. Next, we build a max heap using the negative values of this array, giving us -6, -4, -2, -2. This allows us to efficiently retrieve the largest value. Additionally, we track the smallest value in the array, which is 2 in this case. With the initial setup complete, we initialize our min_deviation to infinity, representing the worst-case scenario. Now, we systematically process the heap by repeatedly popping the largest value, calculating the deviation, and updating the heap. The first value we pop is 6. The deviation between 6 and the smallest value, 2, is 4, so we update min_deviation to 4. Since 6 is even, we divide it by 2 to get 3, push its negative back into the heap, and update the smallest value to 2 if necessary. At this stage, the heap contains -4, -3, -2, -2. When we pop the next maximum value, which is 4, the deviation between 4 and the smallest value, 2, is 2. This is less than the current min_deviation, so we update min_deviation to 2. Since 4 is even, we divide it by 2 to get 2 and push its negative back into the heap. The heap now becomes -3, -2, -2, -2, and the smallest value remains 2. Next, we pop the maximum value, which is 3. The deviation between 3 and 2 is 1, so we update min_deviation to 1. However, since 3 is odd, we cannot reduce it further, and the process ends here. The final result for this example is a minimized deviation of 1. In the second example, we start with the array 4, 1, 5, 23. After normalization, the array becomes 4, 2, 10, 20, 6. Here, odd numbers like 1, 5, and 3 are doubled to make them even. The max heap is built with the negatives of the normalized values, resulting in -20, -6, -10, -4, -2, and the smallest value is 2. Again, we initialize min_deviation to infinity. The first value popped from the heap is 20. The deviation between 20 and the smallest value, 2, is 18, so we update min_deviation to 18. Since 20 is even, we divide it by 2 to get 10 and push its negative back into the heap. The heap becomes -10, -10, -6, -2, -4, and the smallest value remains 2. Next, we pop the maximum value, which is 10. The deviation between 10 and 2 is 8, so we update min_deviation to 8. Since 10 is even, we divide it by 2 to get 5 and push its negative back into the heap. The heap is now -10, -5, -6, -2, -4, and the smallest value remains 2. We pop another 10 from the heap. The deviation remains 8, and since 10 is still even, we divide it by 2 to get 5 and push it back into the heap. The heap becomes -6, -5, -5, -2, -4. Moving forward, we pop the next maximum value, 6. The deviation between 6 and 2 is 4, so we update min_deviation to 4. Since 6 is even, we divide it by 2 to get 3 and push its negative back into the heap. At this point, the heap contains -5, -5, -3, -2, -4, and the smallest value is still 2. Now, we pop the maximum value, which is 5. The deviation between 5 and 2 is 3, so we update min_deviation to 3. Since 5 is odd, we cannot reduce it further, and the process stops here. The final minimized deviation for this example is 3. In the third example, we have the array 10, 4, 3. After normalization, the array becomes 10, 4, 6. The max heap is initialized as -10, -4, -6, and the smallest value is 4. As before, min_deviation is set to infinity. The first value popped from the heap is 10. The deviation between 10 and 4 is 6, so we update min_deviation to 6. Since 10 is even, we divide it by 2 to get 5 and push its negative back into the heap. The heap now contains -6, -4, -5, and the smallest value remains 4. Next, we pop the maximum value, which is 6. The deviation between 6 and 4 is 2, so we update min_deviation to 2. Since 6 is even, we divide it by 2 to get 3 and push it back into the heap. The heap becomes -5, -4, -3, and the smallest value remains 4. Finally, we pop the maximum value, which is 5. The deviation between 5 and 4 is 1, so we update min_deviation to 1. Since 5 is odd, we stop here. The final minimized deviation for this example is 1. The time complexity of this algorithm is O, n*log, max_val, where n represents the size of the input array, and max_val is the largest value in the array after normalization. Normalization ensures that all numbers are made even, simplifying subsequent operations. To break this down, the normalization step involves processing each number in the array. Odd numbers are doubled to make them even, and all values are pushed into the heap. For each of the n elements, the heap insertion operation takes O log n, leading to a total cost of O n*log n for this step. This lays the foundation for efficient heap operations in the next phase of the algorithm. The main computational cost arises from heap operations performed during the iterative process. In each iteration, we extract the maximum value from the heap, which requires O log n for the heap pop operation. We then have this maximum value, if even, and push it back into the heap, which again costs O log n for the heap push operation. Additionally, we update the minimum value in constant time, O1. These steps repeat for every iteration of the loop, which continues until the maximum value becomes odd. At most, this process involves log max_val/min_val divisions per number. For the largest number, this translates to a maximum of log max_val iterations. Combining this with the O log en cost per heap operation, the total complexity of the iterative process becomes O n*log max_val. When combined with the normalization steps O n*log en complexity, the dominant term is O n*log max_val, since log max_val is typically larger than log n for large inputs. The space complexity of the algorithm is O n, and this is primarily due to the heap storage. The heap holds all n elements of the input array, with each value negated to simulate a max heap using Python's min-heap implementation. This requires O n space. Beyond the heap, the algorithm uses a few additional variables such as min_val, min_deviation, max_val, and new_val. These variables are constant in size and do not depend on the input size, contributing only O1 to the overall space usage. Therefore, the dominant factor in space complexity is the heap storage, resulting in a final space complexity of O n. A brute force approach to solving this problem would involve generating all possible combinations of values by repeatedly modifying the array elements. For each combination, we would calculate the maximum and minimum values and their deviation. However, this approach is computationally infeasible as it involves exploring every possible transformation for every element, leading to exponential complexity, 2 to the power of n, or worse. In contrast, the optimized approach leverages normalization, a max heap, and efficient halving operations to reduce unnecessary transformations. By normalizing all numbers to even values initially, the algorithm limits the number of transformations required. The max heap efficiently tracks the largest value in the array, and halving operations are only performed when the largest value is even. These optimizations reduce the time complexity to O and log max_val, making the algorithm scalable and efficient for large input sizes. The algorithm's performance can be analyzed across best, average, and worst-case scenarios. In the best case, all numbers in the array are already even, allowing the loop to terminate quickly. While the time complexity remains O and log max_val, the constant factors are smaller due to fewer iterations. In the average case, which represents most real-world inputs, the array contains a mix of even and odd numbers. This results in a moderate number of halving operations, with the complexity still approximating O and log max_val. In the worst case, all numbers are large and odd, requiring maximum normalization and repeated halving operations. Even in this scenario, the complexity remains O and log max_val, though the number of iterations is at its theoretical maximum. Mathematically, this is explained by the normalization cost of O and log n, followed by the O and log max_val cost of heap operations. With the latter term dominating for large inputs, the algorithm is highly efficient compared to brute force, making it well suited for minimizing deviation in arrays with large values. When solving this problem, there are several common mistakes to watch out for. First, it's easy to mishandle odd numbers. Remember, odd numbers can only be doubled once. After that, they become even and can no longer be modified further. This limitation makes it critical to handle them correctly within the algorithm. Second, the behavior of the priority queue is another area where mistakes are common. You need to simulate a max heap by storing negative values in a min heap, which allows you to efficiently track and reduce the maximum values in the array. Another frequent error is stopping the reduction process too early, specifically when the maximum value becomes odd. While it may seem logical, this can lead to an incomplete solution that overlooks the broader impact on the overall deviation. Additionally, some people attempt to brute force all possible transformations, which is highly inefficient and results in excessive time complexity. Finally, poor initialization of the range, such as not properly setting the minimum and maximum values, can significantly affect how the deviation is calculated, leading to incorrect results. Now, let's explore some key insights and patterns that can help in solving this problem effectively. At its core, this challenge is about minimizing the max-min range of an array using controlled operations. A priority queue, or heap, is essential because it allows you to repeatedly focus on the current maximum value and reduce it strategically. Recognizing this as part of a broader category of optimization problems, those involving range reduction or minimization, is invaluable. Familiarity with heaps and dynamic adjustments will give you a strong foundation for tackling similar problems. Additionally, certain edge cases require special attention, such as arrays consisting entirely of odd numbers, all even numbers, or arrays where all elements are the same. Finally, when explaining your solution in an interview, it's important to communicate trade-offs clearly. For example, emphasize the efficiency of a heap-based solution compared to brute force, which avoids exponential time complexity and operates within O and log n. To strengthen your understanding, consider practicing related problems like LeetCode number 295, which involves median calculation with heaps, or number 239, which uses a max heap pattern for sliding window maximum. There are a few alternative approaches to solving this problem, each with its own strengths and weaknesses. The brute force approach involves trying every possible sequence of operations to find the minimum deviation. While conceptually simple, this method is extremely inefficient for larger arrays due to the exponential growth and possibilities, making it impractical. Another option is to use sorting combined with iterative reduction. In this approach, you first sort the array and then reduce even numbers iteratively while tracking the deviation. However, sorting introduces an n log n complexity upfront, and the iterative steps can involve redundant calculations, making this approach less efficient than others. The most optimal solution is the heap-based optimization. Here, you use a max heap to continually track the largest number in the array, dividing it by 2 repeatedly and dynamically updating the deviation. At the same time, you monitor the smallest value to ensure accurate deviation calculations. This method achieves an efficient n log m complexity, where n is the size of the array and m is the maximum value in the array, making it the best approach for this problem. Thank you for joining me to explore LeetCode problem number 1675, minimize deviation in array. We summarized the key concepts, including the use of heaps and greedy strategies to achieve an efficient solution. Remember, mastering heaps is essential for competitive programming and interviews. If you enjoyed this breakdown, don't forget to like, share, and subscribe for more problem-solving insights. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!